Hi, my name is Parker Kelly, and this is my video going over the report for my Design Assignment 3 project. My group members were Hannah, Edward, Pedro, and Ashley, and the things I did mostly in this group on this project was the Flex. I made kind of the first versions of the Flex. It wasn't the final version we went with, but it helped build to that, as well as I helped out with the report a bit. Firstly, we have to go into the problem definition. So our job was to determine the widths of a positive, negative plates and a dielectric to maximize the capacitance of a high current parallel plate supercapacitor. The values we were given were the negative plate, positive plate, and dielectric's thickness that it must be, the length of them all, the maximum width that they could be, the dielectric's relative permittivity and density, the plate's density, and then the total mass they must be less than. Using these, we had an initial projection of around 29 picofarads. However, we know this is not correct optimized solution, as it also has too high a mass. We just did it with the maximum widths. So then we go into analysis. We took the capacitance formulas and in combination with the electric field and dielectric field formulas to get our capacitance, since our the capacitance formulas are only for areas under and between the plates. However, we are in like a field. Our capacitor makes a field go around it, as can be seen later in our graphs, or our plots, I should say. This is just a visual representation of our capacitor. So we also had to, so the equations we made were the mass equation, since that was one of our constraints. And we did that by getting the volume times density. And this is an example of some code. We based our code mostly off of one of the tutorial or one of the problem set codes. We tried to use the val function to calculate voltage values in each plate. However, we seemed to not quite be working, so we did integration instead. We use those integrals to get our average voltage across the plates, find our delta V's, and then divide our arbitrary charge by that delta V to get our capacitance that we simulated. In validating the model, so we had our boundary calculation space, which we made 0.02 meters greater in all directions. This was the perfect amount of space, since as you can see below in our field plot, everything is perfectly symmetrical. So that means everything, the boundary space is a perfect size. We also have our contour looks very good, and then also in our contour for the electric field, the capacitor is constant. So that makes our simulation seem very valid. Next, we go into scripted and optimization. So what we first did was we found the limits of what we could have using this first function. We then took those and put them into, we got values inside of that using linspace. Taking those, we then ran those through a grid search, and that got our first kind of set of values in our first step towards optimization, which got us this. We then put them to a line of best fit, so using grid search and gradient ascent, we slowly worked our way until we finally got a plot that looks like this. The plots that couldn't calculate, we touch on later in limitations. But this happened due to the fact that AngerGrid couldn't calculate some values that were too small. So, in conclusion, our capacitor seemed to be simulated accurately and realistically. Our optimized capacitance with the chosen widths of 0.021 meters for dielectric, 0.024 meters for positive plate, and 0.013 meters for negative plate, and this resulted in a capacitance of 35.18 picofarads. The limitations we got are due to the AngerGrid couldn't get small enough, and then timeouts.